Welcome back to the garage, guys. In today's video, we're going to show you how to go from part drawing to G-code so you can run your CNC plasma cutter. Without further ado, let's get started. Okay, so the first thing we're going to do is we're just going to go over how to draw a simple part or a simple, something to cut out in your plasma cutter. So the first thing we're going to do is make sure you're in the design workspace. And then we'll go over to sketch. Create sketch, and we're just going to create a sketch in the X and Y plane because those are the axes that the plasma cutter works on. So your X is going to be your red, your Y is going to be green, and Z will be blue. So I'm just going to click on this plane, and next thing I'm going to do, I'm going to draw like the main part of the tab. So I'm going to select 2-point rectangle, and I'm going to assume that we're going to be mating this to 1.5 tube. So I'm going to write in 1.5 inches, and this dimension doesn't really matter now. So I'm just going to drag it out to, let's say, there. Next thing I'm going to do is put a circle and then center diameter circle. Now, an interesting thing you can do is if I hover over this corner and then run my mouse along this edge, you'll see this X with a triangle by it. That's how I know I'm in the center of this line and this line. So I'm just gonna go to here, and I'm gonna go 1.25 inches. Now I'm gonna draw my bolt hole for holding all the parts on, and I'm gonna do the same thing. I'm just gonna drag this out and see this dotted blue line to about here for now, and that'll be 1/2 inch. And then I'm going to go to dimension and dimension these two circles so that the center of this bolt hole and the edge of where the tube will be at will be 1 inch away. So that'll come out to 1 5/8 because I have to dimension from center to center of the circle. Now what I'm going to do is add a center diameter or another circle just to give the tab a nice looking radius. So I'm going to click on the center of this circle and then just drag it to the edge of this one. So it looks kind of goofy now, but it'll all make sense when we do the next step. So I'll finish sketch and then we'll extrude. So this is where we give the part thickness. You can see now that it's starting to look like a tab. So this doesn't really matter because it's a 2-axis machine. You're just plasma cutting. So it can be, 1 inch, whatever you want it to be. But we tend to like to draw our parts in the thickness metal that we're going to be using. So we normally use 3/16. So I'll just type in 3/16. And now I have a completed tab. So now that I have my tab drawn, I don't really want to just cut out one tab because odds are I'm going to be making more than one. So instead of having to run the job, 8 or 16 times over, what you can do is you can copy and orient these the way that they need to be. So I'm going to open the bodies tab. I'm going to right click, copy, and I'm just going to paste that. And so it'll paste it right over top of the next one. So I'll just move it up by 1 3/4 inches so they're nice and close to each other. And this part you're going to have to think about based on what types of material you're using, whether it's just a piece of flat bar or a whole piece of sheet metal. You're going to have to take this into consideration. So let's say I'm using just a piece of flat bar, then I'd maybe want to translate these up or in one direction, whether it be the X or the Y. But if I'm using a piece of sheet metal, I may want to nest them more in a square pattern. So I'm just going to copy 8 more of these, or 8 total. Okay, so now I have all 8 of the bodies or the tabs that I want to cut out, and I'm just going to pretend as if I'm using flat bar. So I translated these in a linear motion in just one direction, and this will be how I put my flat bar on the plasma cutter. Okay, so now that I have all these bodies nested, the next thing I'm going to do is I'm going to enter the manufacturer workspace and make sure that fabrication is set up. Now once I'm here, or the fabrication is selected. Now, once I'm here, I'm going to select setup, new setup, and the machine won't matter. The operation is going to be cutting. The model the orientation, you're going to select model orientation. Since we drew our model in the XY plane, that has already been set up for that. For origin, you're going to have stock box point, and this right here will be your origin point. You can move that just by clicking on these dots here. We typically like to use it in the corner of the stock just because it's fairly easy to get it lined up the right way. Now for stock, we typically use relative size box, but you can also use fixed size box if you were, let's say, loading a whole sheet of metal and you're not taking metal on and off. So I can adjust the width of it here. Let's say I was using a 24 by 24 sheet, and then I would have my select the offset from the X and Y origin, and let's say I wanted this just to be 1/2 inch, then I could move the box over relative to the tabs, and then I could just keep adding more and more parts to this and nesting them without ever having to take the piece of metal off. But for this demonstration, I'm just going to stick with relative size box, as 99% of the time this is what we'll be doing. Post processor, make sure that this is set to 1. We'll go over why this is important later, but you will need this selected as 1. And you can just hit yes, and that's how you make your setup. Notice how we have the little green check mark, so we don't have any errors. Okay, so now that we have our setup made, the next thing we are going to do is make a tool. So we are going to select cutting, 2D profile, and I'm going to select tool. Make sure that your local and library is set up, so these will be your saved tools. You want to select new tool, plasma cutter. The description, I'm just going to call it test tool. You can call it whatever you want. For the cutter, make sure you have plasma cutter set. I'm just going to leave the units in inches. I'll select the kerf width to 1 millimeter. That's typically what ours tends to run at. You'll have to figure out what your plasma cutter runs at once you get your set up. The nozzle clearance diameter will be the distance, or basically the diameter of your nozzle. You want to set this up right, because later we'll be adding a function to prevent the plasma cutter from going over parts that have already been cut, so they won't get stuck anywhere and possibly jam the machine. Ours runs at 20 millimeters, so I'll set it to 20 millimeters. Holder, we don't need to select anything here or do anything with that. Cutting data, this is where you select your feed rate. I'll just leave it at the default for now, but you could set it to whatever you need that to be. Most plasma cutter books, or most plasma cutters will come with a manual that has some recommendations for the speeds that you need to use. Post processor, we don't need to do anything with this, so we'll just accept that and we'll select the test tool. Okay, so now that we have our setup created and our tool selected, the next thing to do is to go over to the geometry tab. This is where you're going to select all the parts that you want to cut. So we're just going to select the boundaries. Okay, so now that I have my boundaries selected, you can see these red arrows. This is going to show the direction and the side that the kerf compensation is going to be using. Generally speaking, you want your red arrow on the outside for outside passes, and on the inside of inside passes to retain your dimensional accuracy. If I click on this arrow, it'll bring this to the inside, and now my kerf compensation will be on the inside. But I'll lose my precision by doing that, so my part will actually be slightly smaller by doing that. So I'll leave this to the outside. Next thing I'm going to do is go to the passes tab. Tolerance, this is pretty self-explanatory. This is how close I'm willing to, or how far I'm willing to be away from the actual body. Setting this tolerance really low will give you a smoother looking part, but it'll also ramp up your lines and you'll have a really big part file. So leaving it at 4/10,000ths, or the default setting, is what we usually do. The sideways compensation, this is an important one. What this does is it'll compensate for cutting on one side of the torch or the other. And this is important because the torch cuts better on one side or the other because it has that swirl ring, or it makes a spiral. So generally most torches cut better on the right side, as does ours. So we'll leave left selected because we want to compensate to the left so that we are cutting on the right. You could see if I select right, now this pass is going the opposite direction. Same with the circle. For center, I'll just be cutting directly on top of the line without compensating anything at all for the kerf. I'll leave this left compensation selected, and we don't need to do anything with stock to leave. But for smoothing on generally bigger parts, you'll want to select smoothing. And what this will do is, instead of making a bunch of individual tiny line segments, it will use an arc to go from point to point, as you can see in the drawing, instead of a bunch of little individual tiny lines. And so this will also help keep your part files down. So we'll select smoothing, and then now we'll go on to linking. Since this is a 2-axis machine, we'll select keep nozzle down. We can have the maximum stay down distance to the maximum travel of the machine, which would be 30 inches. The cut stock clearance, we don't really need to add that or do anything with that, because we already set our nozzle clearance diameter. So we'll just leave that as default. Force retract for inside cut, we can't do that because we don't have a 3-axis machine, so we'll just leave it as is. For lead-ins, so we lead in and lead out. So what that is it'll basically start cutting out here and then come in to the line and then cut along the contours. And this will help you have not such a rough start on the pierce. So what we're going to do is we'll select a pierce radius of, let's say, 0.1 inches. We'll set our sweep angle to 90, and the lead-in distance we'll just leave as is. For piercing, we'll set this to 0. Entry positions, you can select this or not, it doesn't really matter. Basically, we can select on what part of this part here that we are going to start cutting on. I'm just going to leave it in the default. So now we have our tool path created. So you can see the red line down here, the red dot down here is where we start. So we're going to start on the inside cuts and then move to the outside cuts. Now Fusion is normally smart enough to know to cut the inside parts or inside holes before the outside. If that's not the case, then you might have to make another setup with let's say all the holes, not another setup, another toolpath, and then one with the outside bodies. So if I rotate this here, you can see the lines that this is making. So the green lines will be our lead in, lead out. The yellow lines will be our travel moves. And then the blue lines will be the actual cutting. So what I can do to make sure that this looks right is I can select the simulate function and just let it play. And now I can see exactly how the plasma cutter is going to cut this out. And adjust the speed with this here. This is only going to adjust the simulation speed, basically just how fast that's going to run, not the actual machine speed. So once I'm happy with that, we can move on to the next step. Okay, so now that I have the toolpath generated, I still don't actually have code for the machine to read yet. So what I'm going to do now is I'm going to go to select post-process. I'm going to select post-processor from library. I already have this installed. Now there's going to be a link in the description where you can get this post-processor and how to install it. But you need to have this or the machine won't work. And what these post-processors do is they convert your toolpath that we just generated into G-code that your machine can actually read. Now, for simple machines like plasma cutters, they're all kind of more or less the same thing. There's just a little small differences here or there, but you need to have this. So let's say I was using Mach 3 or something like that. I would just select something like Mach 3 plasma, and it'll change the G-code slightly so it can read the Mach 3 board can read it. Now it's not actually going to change the position or anything that the plasma cutter does. It's just going to change it slightly and tweak it so the board can read it, even though it's essentially the same thing. So I'm just going to leave that set here. Your spindle on-off delay is actually going to be your piercing delay, how long the plasma cutter takes to punch through the metal. You're going to have to find out how to set this up for your settings. I'm just going to leave it at 0.6 for now. And I'm just going to call it just test. I'll save it to I could select your output folder here, and then I'll click post. So now that we have the G-code file made, we can open it up and look at it to get a better understanding of what the machine's actually thinking and doing. So just in the comments up here, we can see that the estimated time is 3 minutes and 1 second. And this G90 here means that we're going to use absolute coordinates or absolute movements instead of relative. Okay, next we have the G0 and the G1. These are linear movements. So I believe G1 is the fast movement and then G0 is the slower movement. And we can see that it's telling the machine to go to X 1.765 and Y 0.7235. And then the M3S1000 is the pierce, so that'll tell it to turn the torch on. And then we have a pierce delay of 0.6 seconds, and then we continue to cut. Now the G3 is a arc movement. So instead of moving in individual linear line segments, it's going to move in an arc centered at X 1.02, X negative 0.1 and Y 0. So this is what that smoothing tool did for us. I found the section where it cuts one of the bolt hole circles, and you could see by, instead of using a little tiny individual linear line segments, we can cut this in an arc motion, and instead of using 100 or more lines, we can use under 20 to do the same thing. So it'll help keep our file sizes down, and that'll prevent the machine from bogging and getting jittery. So the M5 that you see here is telling the machine to turn the torch off, and that's more or less it for a plasma cutter. There's not much else you need to know. So one thing I did do here was I pulled the Mach 3 version of this G-code, and here's the Gerbil version of the same toolpath, but just written in different G-code, and you can see it's slightly different. So this is why you need to have that post-processor, because if you try to give the plasma cutter this G-code file here, it won't know how to do anything with it. This is why you need that post-processor so it can read this G-code. Okay, so now that I am connected up to the machine, well, I don't really have the machine with me, I just have the brain right now because I'm traveling. I can't take the whole thing with me. But what I can do is I could still quote jog the machine around. Now, because the machine doesn't actually have servo motors, it has stepper motors, I could still do this, and it doesn't actually know that it's not hooked up. But what I can do is I can open the G-code file, and I've already done this. So you can see the 3D view, and this will be the view, just so you can kind of see what's happening on the machine. Now, I could still jog the machine one way or the other. And the reason why we had to set the work coordinate offset to 1 is for this reason here. So just imagine I have my stock on the machine. I'm going to jog to the machine to that 0 point. Let's say it just happens to be here. I am going to set 0, 0, and now theoretically my tip is right here, and now I can start cutting. So I can actually hit run job, and we can see the coordinates moving and about how long the job's going to take, or the progress that it's actually set. So now I can see that the lines that it's actually set in here, and we can see exactly where it's at. So with that said, that'll be the end of the video. Drop a like if you liked it. Be sure to subscribe if you're new. And if you have any questions, leave them in the comments and we'll get right on it. Thanks for watching.